Hi, welcome to day 2 of Keeping It Real, lesson 4. So this is our do now for today. So if you were not in class, make sure you do it right now. Do now. When it says extract roots, it just means to, what is it called? To simplify. So to simplify the radical, that's what it means. It's just more specific. And so if you don't remember how to do that, remember we're just going to do the prime factorization. I'm going to write that down. So prime factorization. That's a thing. So prime factorization of 48, which means what? We're going to find all the numbers that multiply to 48 that are just prime. So in other words, like 2. So 2 goes into 48 how many times? 24 times. 2 goes into 24 12 times, and you just keep on going, like what goes into 12? Well, 2 goes into 12. And you just kind of keep on using 12. And with 12, 2, just keep on using 2. And if 2 doesn't work, then you use 3. If 3 doesn't work, use another prime number like 5 or 7. I usually start with 2 and 3. So 2 goes into 12 6 times, 2 goes into 6 3 times, and 3 goes into 3 once. So we just go until you hit to a 1. So if you take a look at these right here, we're literally saying that underneath the square root is 2 times 2 times 2 times 2 times 3. Right? This, which is equal to 48. That's where we're getting these numbers from. Okay, so all of it has to equal to 48, which is our first problem. And if you notice right there, we have, when we talk about square roots, we're looking for perfect squares. The only way we could get a perfect square is if we have two numbers that are multiplying it by itself, multiplying together by, to get another number. That makes no sense. Do you know what I mean? And so like 2 times 2 is 4. And what's the square root of 4? 2, right? Those are perfect squares. So we're looking for perfect squares. So here it goes. So this is the 2 squared. This is 2 squared, and this is also 2 squared. And what do we get if we square root of 2 squared? 2, right? So all we have left, so we're going to be square rooting those guys, because remember, those are under the square roots. And what do we have left? It's 2. 2 times 2 is 4, and that's how we got the 4. And then this is square root of 3. Notice that it's inside the square root, and it can't come out because it's not a perfect square. Because if I ask you what's the square root of 3, and you'd be like 1 point something, and I'll be like, yes, correct, right? And so it's not a perfect square, so it just stays in at the square root. That's it. All right. And so the other numbers are going to be 3 root 3, and square root of 32 is 4 root 2. Okay. Another way to think about it, for square root of 32, you can be like, oh, well, 16 times 2 is equal to 32. And we're like, well, 16 is a perfect square. So what's the square root of 16? 4. And 2 is not a perfect square, so we just leave it there. And 2, we can't simplify that any more than what it is. So there it is, 4 root 2. That's it. Okay, other ways to think. So if you can pull out perfect squares, that'll probably be the most simple for you. But if you can't think of them, go with prime factorization. You could either use the factor tree or this upside down division method. Maybe we'll call it the ladder method, right? I think that's what some people call it. And so for day 2, we're going to be doing this purple stuff right here. So extract roots from the radicals, and rewrite radicals by extracting roots. This is pretty much the same thing. We're just basically going to be simplifying radicals in layman's terms. Extracting roots sounds like, as I said before, dental work, right? So we're going to do a little bit of fast forwarding because we've already passed through this part. And we're going to go into yes, and if you missed this section, go to the previous video. It's all there. All right, so here we go. So extracting roots to rewrite radicals. So in one of my classes, we talked about this left-hand side, and this left-hand side, this using radicals and using powers is actually quite mathematical and really good. However, it gets really confusing if you're not really comfortable with cube roots and fourth roots and et cetera, et cetera. They're like, what? So I like to do it my visual way, because the visual way for me works out a lot better. So let's see if we can do that. All right, so if we take a look at their problem, which is the cube root of 8 times x to the 6th power. So if you take a look at this guy right here, what we're going to do is we're going to do the prime factorization of 8. So if you notice right there, we did that. So we said that 2 goes into 8 4 times, then 2 goes into 4 2 times, then 2 goes into 2 once. And so it's 2 times 2 times 2. So note, well, what is the cube root of 2 cubed? Right, because 2 times 2 times 2 is 2 cubed, right? So which is going to be just 2, right? So this is 8 is actually a perfect cube, right? It's because 2 times 2 times 2 is 8, right? So the cube root of 8 is just 2. Okay, and then well, what about the x to the 6th power? If you look at right here, I wrote it all, I expanded it, right? And so, well, remember here, the index is telling us, well, how many of each kind do we need? So we need 3 of a kind, right? So we have 3 x's here, and we have another 3 x's here. So how many groups is that? It's 2 groups, right? So if it's 2 groups, then that's why we get the x squared. Or if you want to think about it more mathematically, well, x cubed, right? X times x times x is x cubed. And then we got to cube root it. So what do we have left? Just x. And then the same thing with this one. So it's x times x, which is x squared. And notice everything was a perfect cube. So that's why we have no more cube roots. Then we used them all. So 2x squared is the simplified version of that above. Right? And if you notice, that's what they got too. Yay, happy days. So we're going to try that for Embry and Devon, same kind of problem. So this is the problem that they had. So this the 4th root of j to the 8th times k to the 4th, right? And so if you take a look at here, I wrote down 8 j's and 4 k's, right? And how many groups of 4? Now I'm looking for groups of 4 because it tells me it's the 4th root, right? So that tells me how many are in each group, right? So that's going to be, excuse me. So I have 2 j's here. So remember it's j to the 4th, and we're going to 4th root that because it's inside the 4th root. So the 4th root and the 4 cancels out, and all we have left is j, right? Same thing with the other group. So it's j times j, which we get j squared. Okay, so that is my yellow j squared right there. And if we look at the k's, like, okay, so there's one group of 4 k's, right? And k to the 4th, and we 4th root that those cancel out, and we get left as k. Now you got to remember, these are 4th roots, right? Which means that we cannot have any negative answers. It can't happen. So, I mean that. So if you notice here, we have to put the absolute values around the k. And you may wonder, well, why not about the j squared, right? The j squared is always going to be positive, right? Because j times j, so if it's a negative times negative. So if j is negative, it's still going to be positive because we're squaring it, right? So since we're squaring it, you don't need to, but you could, if you really wanted to, put an absolute value around the whole thing, you know, but that would be a little redundant for the j squared because j squared is always going to be positive. So this would be the better way. But if you do the absolute value of j squared times k, that's not wrong, right? It's still going to give you a positive answer. And if you notice right here, this is how they wrote it, like how we wrote it initially, which is good. And again, if you want to take a look at what they're doing there, what they're doing is it's also very mathematical, but this is mathematical as well. What we're doing is just more visual. I don't know how you would have done this in like a book, right? But yes, they're using with exponents, right? And using the power of exponents to figure that out. And if you notice right here, we're just taking that form, we're dividing it, but this is why that works, okay? And we're gonna go into Betty, Wilma, and Rose. So the question was, who's right, Betty, Wilma, or Rose, or or Rose? It could be any combination of that. And ignore the stars, pretend we're not even there. All right, so we got the square root of x squared times y squared. And notice when we have a square root, we don't put any number in there because when we're thinking what square means 2, right? So that is going to be, the index is always 2, right? If it's invisible, it's 2. If we mean something else, it's going to be that other number that we put in there, right? And so if you notice right here, I wrote them out like this. So this would just be x squared. The square root of x squared is just what? X. The square root of y squared is just going to be y. So your answer is just xy. And if you were paying attention, you'd be like, wait a minute. There are there's a restrictions on that, right? Because it is square root. And So you are going to have to put in the absolute values. The question is where. And if you take a look at this guy right here, so if we do the absolute value of x times the absolute value of y, we will always get a positive answer, right? And this in orange was our example. Like, what if x was -2, and what if what if y was 4? What if, right? And this is how you can find your counterexample, right? X and y, what is x and y? They're just numbers. They could be any number. They represent any number. And that's why we need to put in these absolute values, because x could be negative or y could be negative. And if they're both negative, then we don't really have a problem because the negatives will cancel out. But what if one of them is positive, one of them is negative? We have to take into account for that circumstance, that situation. So either Betty or Wilma, either way is okay. The annotation is fine, because eventually you'll get a positive answer, right? Because x times y, and then you do the absolute value, still will give you a positive answer, right? But the problem with the roses is that x times y, what if x was -2 and y was 4? Then what? Then x times y it gives you a negative answer, and we cannot have that, because in a square root, we can't have negative answers. Alrighty, so here we go. So that's going to reduce down whatever. Let's see here. So where was I? Oh yeah, so Betty and Wilma are good, and some people were wondering, well, why do we have all these restrictions anyways? If you remember back to lesson 1, we were doing like a lot of these invertings. I have them right here. Where's my other one? So if you remember this, you remember doing this? It's a good thing I don't throw these away. And so remember the parabola, when we flip it, right? Remember how it was not a function? I don't know if you can see that. It was not a function because of this bottom part right here. We needed to get rid of that. So what is this part? That's the left-hand side. That's where x is negative, right? So we needed to restrict that. We need to say, no, we can't have that, or else this is going to be not a function. Can't have that. So if you notice right here, excuse me. So that's why for any of the even ones, we need to say that x has to be greater than or equal to 0, or just x is positive. So absolute values. Okay. And then remember for the, I do it this way, for the cubics, which it represents like the odd powers, right? And if we do the inverse, it's still a function. So we didn't have to have any restrictions because the inverse is still a function, right? So therefore, odd ones, odd roots, no restrictions, don't care. Okay. So we did the same thing for these guys right here. So the square root of m to the 4th over n to the 6th. And in your brain, you're like, okay, I can do this without drawing it. You totally write it up if you want to. So m to the 4th. The square root of that is just m squared, because we have 4, so that's 2 and 2. So that's 2 groups, right? Or you can just think 4 divided by 2 is that m squared, and then n to the 6th, the square root of n to the 6th is going to be n cubed, right? And we do need to have restrictions on the bottom one, because n cubed could be negative. It's possible, right? If n was a negative number, then it would be negative, but we can't have that, because remember, our root is a square root. It's even, right? So we need to restrict that. So that's why we put the absolute values there. And if you notice, we don't have it for the top because, again, it's going to be positive anyways. It doesn't matter. Okay. And, or you could, if you want to do just the whole thing as be the absolute value, you can do that as well. This is just more exact. Okay. Makes you look smarter. All right. And if you take a look at B, right? So the j to the 12th power, we're going to go 12 divided by 3, which is 4, right? Because we're looking for groups of 3. How many groups of 3 do we have? 4 of them. 12 divided by 3. And then 3 divided by 3 is 1. And so the question was, do we need to have absolute values here? That was the question in class. Some people said yes, some people said no. And remember, this was an odd, so this is cubic. It's a cube root, which means that, yeah, the inverse is a function. There's no restrictions. So at k can be negative. It's fine. Okay. So this is the answer for that. All right, now we're going to go to Bernadette and Chris. So Bernadette and Chris, if you notice right here, they have the right answer. They're like, yes, we did it right. They did it in different ways, right? One did use them all as changed everything to exponents, while this one they're keeping with the radicals. but they do get this answer, right? And then we're going to take a look at how they got that answer. So if you look over here, this is their problem. So the cube root of 16x to the 8th power. I'm just going to do a prime factorization of 16 because I don't know what the cube root of 16 is, like, right? And so we're going to go, so it's 2 times 2 times 2 times 2. So I noticed that we have one group of 3, right? We're looking for 3s because that's our index, cube root 3s, right? So that's one group. So that's the 2 right out here. So what do I have left over? This 2, the C in the pink, that stays in the cube root because it's not a perfect cube. So it just stays in the cube root. All right. And then we're looking at the x's. I have 8 of them, right? Here's my 8. And I notice that there are 2 groups of 3s that we have here. So this is going to be 2 groups. So remember, this is like x times x, because if we cube root the cube, it's just going to be x, right? So it's x times x, which is x squared, right? And then what do I have left over is 2 x's, which would be x squared. So notice that this x squared and this x squared seem to be the exact same. You're like, so it's the same thing. So you only have 4 x's. That doesn't make any sense, right? And you got to remember that this x squared means, remember, it's 2 groups of 3 x's, right? We have the 2 groups of 3 x's, and this right here is just 2 x's. 2 x's left, right? That's these guys right here. So I try to color coordinate them, so take note of that. Look at the colors. So that's what that means. Ooh, in my class, somebody had mentioned, and I thought this was very clever. If you want to check this, right? So remember we cubed it, right? So I'm going to just cube the 2. So 2 cubed is 2, 4, 8. 8 times 2, which is going to be 16. Right? And then this one's cubed. So 2 cubed, which is 6. So, well, this is not as easy. But if we go back, I'm going to go back because this one was a good one. I really liked it a lot. Let's go back to the do now. I was like, I need to mention that, but forgot to mention that. So if you go look back here again, remember this was going to be 3 square root of 3 for the square root of 27. A good way to check that is you just do the reverse of it, right? You cube the 3 on the outside, right? And then that's going to be, so 3 squared cubed. You square the, no, because we're talking about square roots here. So 3 squared is 9, and then 9 times 3 is 27. So do you see, it should give you that same number, like back. So again, 4 squared is 16. 16 times 3 is 48. And right here, same thing here. So 4 squared and times 2, that will give you the 32. So I thought that was a good way to check that. All right. So moving back to where we were. Ooh, this is like almost exactly where we were. Excellent. So if you take a look at this, I said we would go over this. So here we go. We're going over it. Please make sure you do these first, try them out first, and then press play. So right now, press pause. Seriously, press pause. All right, so here we go. Now that you've done all of them, A through H, we'll just go over them. So if you look, so I'm thinking, okay, square root of 16. Well, I know what the square root of 16 is. It's 4, right? So if you want to do the prime factorization of that, you totally can. Or you can just be like, well, I know what that is. It's 4. So, you know, we'll just go with that. And then x to the 6th power. Remember, there are 6 x's. How many groups of 2 do I have? 1, 2, 3. 3 groups. So that's going to be x cubed. Right? So that's the answer you should have gotten. However, remember, this is square root. So you need to add in. So the 4 is always going to be a positive, right? Because that's what 4 is. There we go. That's going to be x cubed. X cubed has to have the absolute value because remember, it could be negative. It's possible. So we need to prevent that. So we need to make sure that it's always positive and put in those absolute values. All right, number B. So the negative is on the outside. So we're fine with that. And so what is the square root of 8? Ooh, it's not a perfect square. So I'm going to be like, okay, so here's 8. Here's 4 times 2. Here's 2 times 2. So 2 times 2 times 2, right? There's 3 2s, which means 2 of them make a perfect square. So what I'm going to have is I'm going to copy that negative down. 2's go on the outside. I'm going to put a little room right here. And the 2 is going to go on the inside. Okay. So I'm going to see if I could color coordinate this. So this 2 right here is this 2 right here. And this leftover one that's staying inside, is right in here, staying inside the square root. All right, and let's look at the V's. There are 3 V's. So I have, how many groups of V's do I have? I have 1 group, goes right here. And then the leftover goes there. I just got to make sure I extend the square root so it's covers that. So that would be my answer. So negative 2V square root of 2V. Okay, only thing is, remember, we're talking about square roots. So I know there's that negative out there, and we can leave that, okay, because leave that be, but we know that this V cannot be cannot be negative, okay? So we have to put in the square root, because ultimately this answer will always be negative, right? Because what is the square root always going to be? A positive number, whatever positive number it is, well, including 0. And then we're going to just negate that. We're just going to make that into a 0, into a negative. Okay, so we got to ensure that this V remains positive. You know, you have to look at it really carefully and think about it. Okay, so again here, so what is this one going to be? So we got 3 D's. Let me just put my square root right here. So D is going to come outside. So I have 3. So got 1 pair that comes outside, and then one of them stays inside. And then we got V to the 4th, or F to the 4th. That means I got 2 groups, right? So that's going to be F squared. And no F's inside. So because all of it was a perfect square. So that's what we're left with. Any absolute values? Yep, we do. So we need to add in those absolute values right here for the D on the outside. That's it. That's the only one we need. Make sure that is positive. So same thing with D right here, this D. So this is going to be H squared, and this can be J to the 3rd power, right? Which one needs the absolute value? The J cubed. H squared is always going to be positive, so it doesn't matter. And then right here, this is going to be, so again, these are all square roots from A through E. So all of them, we need to think about those restrictions. When we get to G, yeah, then we don't have to worry about it, but F and H, they both need it as well. So the square root of 25 is 5. So you should get a 5. Square root of A, square root of A squared is A, and then B to the 4th, and then C to the 5th. And honestly, at this point, I would just be like, okay, put absolute value on all of that, right? But if you want to be more technical about it, this is, oops, I erased something. Should be 5. So you would need an absolute value around A as well as C, right? But now it's just a whole bunch of lines reading between the lines, right? So that's where the absolute values would go, but you could just put the absolute value around the whole thing. Be like, call it a day. All right, 81 to the 4th power, or the 4th root. Ooh, what's 81 to the 4th root? So if I'm looking over here, 81 is 9 times 9, and that's going to be 3 times 3 for all of them. Oh, so the 4th root is 3. Great. So we got 3, and then so that's going to be, if we have 5 x's, right? How many of them are going to be in a group of 4? 1 group, and then we have 1 left over. So there's 1 group out here, and then we're going to have our 4th root with our x inside, okay? And then y to the 12th, we can have an even number of groups, right? How many? 3 groups. So it's going to be y to the 3rd power. Remember, this is 4th root, so it can be like, yeah, because x could be negative and y to the 3rd power could be negative. So that's why we have to put the absolute values around both of those guys. If you do want to do them separately, you can totally do that, or you can just do it like this. And let's take a look at G. G is, remember, we have x plus 3, x plus 3, x plus 3. We have 9 of them, right? So how many groups of x plus 3s can we get? 3. So this is going to be x plus 3 cubed. All right. And then, and again, no, we don't need any absolute values because this is a cube root, right? It's odd. So those are all functions, no restrictions. So if you take a look at this guy, we have x plus 3 squared, and the square root of that, well, the square and the square root, they cancel each other out. So we get x plus 3. Remember, always has to be positive. So we have to put that in there. Okie dokies. Now we're going to the next day. We don't want that. So, and there we go. Hopefully this was helpful for you, and I will talk to you guys later. Bye.